In this video, we're going to see if we can find the inflection points, if there is or are any, for this function here. F of x equals x cubed minus 18x squared plus 96x plus 14. So if we have an inflection point, by definition, we want to see if the concavity of the graph changes at some point. Does it change from concave up to concave down? Or does it change from concave down to concave up? This is equivalent to seeing if the sign of the second derivative changes at some point. Remember, the second derivative tells us about concavity. If the second derivative is positive, then the graph is concave up at that point. If the second derivative is negative at a particular point, then the graph is concave down at that point. So if we can check any points where the sign of the derivative changes, we can potentially determine whether or not we have an inflection point. So because the second derivative is key here, we're going to start taking some derivatives. Here's our original function. The first derivative looks like this. The derivative of x cubed is 3x squared. The derivative of negative 18x squared is 2 times negative 18 is negative 36 times x to the 1. The derivative of 96x is 96, and the derivative of this constant is 0. That's the first derivative. But remember, we're talking about concavity, so we need to keep going and take the second derivative. Taking the derivative of 3x squared now gives us 6x, and taking the derivative of negative 36x gives us negative 36. And of course, derivative of 96 is 0. So this is our second derivative. If we have an inflection point anywhere, we need to find out when the sign of this expression here can change from positive to negative or negative to positive. When does that value change, its sign? The only time it's going to change its sign is across the point 0, across the value 0. So essentially what we can do is we can say, well, when is the second derivative equal to 0? So if we set that expression equal to 0 and then do some quick algebra, you can do that and see that x equals 6 is the only point where the second derivative, this expression right here, 6x minus 36, is equal to 0. So if the sign of this expression is going to change at all, it's going to be right at this point. So our strategy will be to simply take a look at a point to the left of x equals 6 first. We'll make it easy. Let's choose one unit to the left, x equals 5. And then we say, what is the value of the second derivative at 5? So we plug in 5 into the second derivative up here. 6 times 5 is 30. 30 minus 36 is negative 6. That's 0. So the second derivative at 5 is negative, which tells us that we are concave down to the left of 5. So everywhere from negative infinity all the way up to 5, this is a concave down graph. Now we're going to look at a point to the right of x equals 6. Let's take 7. Take the 7 and plug it into the second derivative. So 6x minus 36 becomes 6 times 7, which is 42. 42 minus 36 is actually 6. There's a little typo there. But it doesn't matter because the value of the derivative there is positive. So if the second derivative at 7 is positive, then the graph is concave up there. And so now we see that because the concavity is changing from down to up, then x equals 6 is indeed an inflection point. And that's our conclusion. Now, so that is our conclusion. So let's just imagine what would happen if we had found out for some reason that to the right of x equals 6, we also had another negative value. In other words, to the right, we would have a concave down graph. And we hadn't changed from concave down to concave up, then that would not have been an inflection point. The only way we can The only reason that we can conclude that we do have an inflection point is because we saw the change in sign from negative to positive, and therefore from concave down to concave up.